So the only real difference on this part of the activity compared to the one that we just did is they just changed the geometry of our water tank a little bit. So instead of a cone, now we have a sphere. So it looks like this, say. And instead of filling up the tank, this time we are draining the tank. So let me try and sketch in a diagram that conveys that here real quick. So here's my tank. It starts full, and then it begins to drain. So let's just imagine that it's been draining for a little while. And here's the surface of the water, and then the rest of the tank is sort of filled up here. Okay. But what we know about the nature of the relationship in these quantities is the same, right? How is the tank draining? What do we know about the rate at which the water is coming out of the tank here?
Constant.
It's constant. Again, they've given away the game kind of in how they've set up the problem, that there is a constant 1.2 cubic feet per minute rate at which the water is draining out of this tank that's given to us right here, and that remains constant from the beginning of the draining process to the end of the draining process. And what did that do in the shapes of your graphs? How is that reflected in the shapes of the graphs that you drew? It went down, and how did it go down? Yeah, it went down in a straight line, a linear function, right? So when you sketched the graph of volume versus time, you probably got something that looked like that-ish, right? Not exactly to 100 over here, but you get the idea, I hope. There we go. And so again, the reason for that, and I'm going to give us a little preview of section 1.3 for just a moment, because you're going to be reading that between now and Wednesday. So let's say I take two of my observations from the data table on this side. So after 20 minutes, what was the volume that you had here? What did you write down for the 20-minute volume? 89.1. 89.1. And that's being measured here in cubic feet. And then let's say after 60 minutes, what was your observation there?
41.
Point anything? 0.0? Ish. Okay. All right. So we'll make it as roundy as we need to. Okay. So let's say I have just those 2 points, and I just picked those two at random. Each of those corresponds to a point on my graph, right? Here's my point with coordinates 20, 89.1. 89.1. Right? That's this ordered pair on my graph. And the other point, 60, 41.0, that's a point over here where t is equal to 60 and v is equal to 41.0. So that's about here. 41.0 and 60 is the horizontal coordinate. Okay. So if I were to ask you between the 20-minute mark and the 60-minute mark, what is the rate at which the water drained over that period of time? What would you say is the rate at which the water drained over that period between 20 and 60 minutes? 1.2 cubic feet per minute, exactly. So where did that number come from? Yeah, that came from the constant rate at which the water was draining. Now, my question is, if I ask the same question about the period of time in between 40 minutes and 94 minutes, what would the rate be over that time? The same. In fact, any 2 points that I pick, we're going to get the same rate, right? Because the rate is constant at which the volume is changing with respect to time, right? So how would I get that rate? How would I recover that rate out of the data that I have here? Where is my 1.2 in this data table? Where is my 1.2 in this graph? What does that 1.2 correspond to? It corresponds to, on the graph, the slope. So yes, this little line segment here that joins my 2 data points, that line segment is going to have a slope of 1.2. 1.2. And the units of that slope would just be, well, every slope is a rise divided by a run, right? And so the units are going to be the units of the rise, that's cubic feet, divided by the units of the run, t. T is measured in minutes. So sure enough, the units of my slope also work out to be the units of the rate that we were expecting, right? And again, why is this graph a straight line? Because what can we say about that slope? It's constant. any 2 points that I pick are going to be connected by a line that has the same 1.2 slope. Right? So the slope is 1.2 on the graph, and that number could have come from my data table as rise divided by run, right? The rise is the difference, 89.1 minus 41.0, which, what's that going to be? 48.0. And the run is just what I get when I subtract 20 minus 60. It's going to be negative 40. And if I divide rise divided by run, I get a slope. After all, that is what slope means. Right? So rise divided by run. So I'm going to get here 48.0 cubic feet, right? Because that's what the units of these quantities were. Divided by negative 40 minutes, which is a little bit weird to see a time measured in negative numbers. Might want to think about what's going on there. But when I divide these two, 48.0 divided by negative 40, hey, look, negative 1.2. And the units come across, cubic feet over minutes. Right? And so that's where that number comes from my data table. What's that negative sign doing?
It's representing the removal, the draining of the water.
Right. It's representing not just the amount of water that's changing over time, but also which direction that change is happening, right? Here the tank is draining, and so the volume of water is doing what as time goes on? Decreasing. Exactly. And that's actually the legit mathematical word we're going to use for a situation in which the rate of change is a negative number. Okay? We will say it's decreasing because as one of my quantities goes up, so as time goes up, the other quantity goes down. So as I move to the right on my graph, I'm also moving downward, right, for a decreasing relationship. In an increasing relationship, the opposite is true. Right? If I move to the right, I go up. If I move to the left, I go down for an increasing relationship. So yeah, that's a good way to interpret the meaning of this minus sign. It just tells me that this is the rate at which the volume of my water is decreasing. Okay? So what about this last part where you're asked to speculate how the height changes over this time? So what kinds of shapes did your graphs have for height versus time? So when the tank is full, what is the height of the water?
It's at the maximum.
It's at the maximum. It turns out to be 6 feet in this example, so we'll just sort of label it there. So that's where it starts. And when the tank is empty, after however many, 94.24 minutes, right, then what point on my graph does that correspond to?
The lowest point.
The lowest point.
And
So
at the end of the time as well.
yeah, 94.24, right? Okay. And so somehow my height graph has to connect to this point to that point. But as you're telling me, it's not going to do that with a straight line. What kind of a shape does it connect with?
I would call it like an S.
Yeah, a little sort of a wavy S. If we're being really, if we like terms, and I like terms, we call it a sigmoidal shape. Sigmoidal, yeah, right. So I saw a lot of shapes that look kind of like this in the groups. Do I have that right? Sigmoidal.
Is that spelled like how you imagine it?
Sigmoid, yeah. Well, and it's just so sigmoid being from the Greek letter sigma, which is the letter S, right? So this just means S-shaped. Right? Okay, so where'd you come up with this? So what's going on in this graph that's important? And how do you know it's doing that?
Well, it starts pretty steep and then it
Okay.
kind of flattens off and becomes steeper again.
Okay, so what is happening in my tank when this rate of change is steep? Yeah.
It's steeper when the water at the sphere is like at a smaller surface area.
Well, yeah, when it's at a smaller surface area, when it's a kind of a narrower portion of the sphere, then taking out the same amount of volume is going to change the height more quickly, right? So up near, when the surface of my water is near the top of my tank, the height is changing relatively quickly as the tank drains. Whereas if I'm kind of here in the middle, then taking out 1.2 cubic feet is going to take out some height at a slightly slower rate, right? And so we do get this sort of sigmoidal shape. Here's a question. Is there anything about this graph that could tell me that the top of the sphere and the bottom of the sphere are the same shape as one another? talking about symmetry here.
Yeah, in the sense that it will have the same rate of decrease at the beginning of
Mhm.
the time and at the end of the time.
And at the end. So at any given level, so right here, let's say, right, whatever the rate of decrease of the height is at this point, where is the same rate going to happen again?
At basically the same level.
The same point on the other side of the hemisphere, right? So there's a symmetry to the shape of this graph that we're going to, in a few sections from now, call odd symmetry. If I just take this piece of the graph, and what's the middle point, by the way? What's happening at the very middle point of this graph? Where is the water?
It's where the sphere is at its widest.
It's where the sphere is at its widest. This is the equator, right? When the tank is half empty. Right? But if I take this portion of the graph and I just sort of cut it out and I paste it upside down, I get exactly that shape that's on the other side of it. Right? So that's a reflection of the symmetry of this. So